Hello, chemistry class. Today we are going to be exploring gases and the atmosphere. In particular, we're going to be exploring the history of our atmosphere. Now, a lot of you might be thinking, well, Mr. Saul, I know what the atmosphere is made out of. Right? We got nitrogen, we got oxygen, we got carbon dioxide, methane, water. But it wasn't always that way. Prior to about 3.5 billion years ago, our atmosphere was mainly composed of water, methane, and ammonia. Now, these different reagents, we'll call them, were essential to building early biomolecules, things like amino acids and RNA. A very famous experiment, if you want to check it out, is the Urey-Miller experiment, where they took the conditions of our early atmosphere and they showed that in a laboratory setting you could create these biomolecules that were essential for early life. Amino acids, the building blocks of proteins, and basic nucleotides, mainly of RNA. So the earliest life on Earth was likely RNA-based. Now over time, nitrogen and carbon dioxide began to build up in the atmosphere due to the outgassing of volcanoes. Keep in mind that our early Earth was still a very non-hospitable place to life. There was much more volcanic activity. And another important thing to note is there was very, very little free oxygen. The atmosphere at this time was a reducing atmosphere. The atmosphere we have today is an oxidizing atmosphere. I wonder why they call it that. Could it be because now we have a lot of oxygen in our atmosphere? Now, the earliest evidence of life is from approximately 3.5 billion years ago. And we know this because we've found fossils. We've found fossilized ancient microbes in places like Australia, for example. But more importantly for our purposes, we know that photosynthetic life, life that could utilize the sun's energy, water and carbon dioxide and make sugar, we know that that life evolved 2.7 billion years ago. What is one of the byproducts of photosynthesis? Hint. Yeah, it's oxygen, right? It's oxygen. So oxygen started to build up in our atmosphere as this life proliferated. Now, these cyanobacteria here, we don't know that they arose 2.7 billion years ago because of some fossil. We know this for another reason. What could that reason be? Well, let me ask you a different question. What happens when you combine water, iron, and oxygen? You've seen it on cars in the springtime as all that snow melts, all that salt gets all over your car. What do you see? Yeah, that's right, you see rust, right? You see rust. So what do you think we see when we look at rocks that are 2.7 billion years old? Well, we see a giant iron band across our planet, a giant rust band, these red rust streaks in rocks that are 2.7 billion years old. So that's how we know when oxygen first arose on Earth, or free oxygen, I should say. Now, as the amount of free oxygen began to increase, due to reactions in our upper atmosphere, we began to develop an ozone layer, which was huge for life on Earth. Because what does our ozone layer do? Right? What does it do? It blocks that UV radiation. The radiation that's so dangerous to nucleic acids, to DNA and RNA. This allowed the integrity of genetic information, right? It wasn't as easily corrupted. It allowed more complex life on Earth to develop. Now, let me ask you a different question. What is our legislative building made out of? What is it made of? It's a very famous stone, famous to Manitoba. We have a place named after it. It's made of Tyndall stone, right? Tyndall stone is a type of limestone, a type of sedimentary rock. Interestingly, maybe you went there when you were a kid and you've seen this, but if you haven't, next time you go there, I recommend you check out the rocks. In these rocks, you can actually see fossils. And next time you're at FRC, you can see them as well. The Tyndall stone, or the limestone that's on the back of our school, it actually has a lot of interesting fossils to see. There's trilobites and other little critters of that era. So next time you're here, I do recommend you check it out. But essentially, those stones are the remnants of ancient dead stuff. Now, why am I telling you this? Well, that's where the majority of carbon on Earth is stored. It's stored in ancient dead stuff. Sedimentary rocks are fossil fuels. Now, this is a graph of how carbon dioxide has changed through geological history. Now, we have very accurate evidence for a long period of time, 100,000 years. And that very accurate evidence is mainly based on ice core samples. So we drill ice core samples in Antarctica, we look at little tiny gas bubbles trapped within the ice, and we can actually analyze what the atmosphere was like during that period of time. Now, you can see that over the past 400,000 years, we think that there was a pretty steady cycle. There's cold periods and there was hot periods, right? Hot periods where the higher concentrations of CO2 are, and ice ages where the CO2 levels drop here. Now, one thing you see at the end of this graph is this giant jut upwards, right? It shoots off the graph. That represents what we've been doing to our atmosphere. We have been radically increasing the amount of carbon dioxide in our atmosphere. Now, when I talk about climate science, people often like to point out, hey, Mr. Salt, the atmosphere was warmer at points in the past. And they're not wrong. However, what we're really concerned about as scientists is that the rate of change is so great that animals can't adapt. Life is having trouble adapting to this very rapidly changing climate. Climate change compiled onto that are ever encroaching into natural habitats, our overexploitation of our seas and our land animals, and we have a recipe for disaster, and we're seeing that now. The extinction rate today is so much higher than background levels that we've entered the 6th major extinction on our planet, what we've called the Anthropocene extinction, the human-caused extinction. Now, if you haven't had a chance to watch those IPCC videos on my website, I highly recommend you do. They are very, very good at explaining how dire the consequences are if we do not change our ways. I also recommend you watch this one here as well. It's kind of a cute little parody on what we're doing to our Earth. Now, what is the atmosphere composed of today? Well, the atmosphere is composed of about 78% nitrogen, 21-ish% oxygen, 0.93% argon, 0.039% carbon dioxide, and other trace gases like methane. Now you might be saying to yourself, Mr. Salt, that number is really, really small. 0.039% carbon dioxide. Why are we making such a big deal about it? Well, let's look at the solar system for examples of what would happen if we didn't have carbon dioxide in our atmosphere. Now, if we look at planets that don't have an atmosphere, or even like our moon, for example, the temperature swings from day to night are wild, right? They swing hundreds of degrees. And without carbon dioxide in our atmosphere, we'd effectively be a giant ball of ice. We need the greenhouse effect to keep our planet livable. But the issue is, if too much carbon dioxide builds up, well, it can become too hot to live. That's obviously an extreme, but we can look at other planets in our solar system and ask some very pertinent questions. Like if you look at, for example, Mercury and Venus, which one's closer to the sun? Well, Mercury is. But let me ask you a different question. Which one's hotter? Which one has a hotter surface temperature? It's actually Venus. Why is it Venus? Well, Venus has a very thick atmosphere full of greenhouse gases, and it is way, way, way hotter than Mercury as a result. Right on. Have a good day, everyone.